Hi, my name is David Blewett. I am the senior developer for the CrowdStrike Operations Center. CrowdStrike is a computer security startup that has a Windows and OS X kernel driver that pushes up real-time data for all events that are happening on a set of given nodes. And we use ZMQ to route that data all over. Anybody that needs to connect to it, consume it, is most likely using ZMQ to do that. So today we're going to talk about how to get started with ZMQ, the basics, building blocks of it. I'll talk a little bit about what it is, what it's not, some common patterns, transports, the process that is recommended in the Z guide for building a distributed app and what we have followed. Some examples of coding using ZMQ in a couple different ways in Python, and some of the best practices that my team has found over the last 6 months or so. And then finally I'll end with an example diagram of a working ZMQ pipeline that's currently processing. So what is it? It's built as a concurrency framework so that it abstracts the inter-process communication between any set of given nodes. And the nice thing about it is that it provides a set of patterns that you can easily plug into and use out of the box without a lot of extra effort. It has a concept of atomic messages so that a receiving side can't start processing something until the complete message has been delivered from the sending side. And the last point is pretty key. It's language agnostic. There's bindings for it for just about every given programming language, so that if you hit a spot in your processing pipeline that really requires extra speed, you can use C or Go or something else that if Python can cut the mustard. I haven't hit that yet. I'll discuss that in a little bit, but we have a pretty high throughput going through Python. This slide, it describes a couple of the patterns. There is a request-reply pattern, but I wouldn't recommend using it. There's some broken behavior that there's a blog post by Armin Ronecker that really talks about it, and there's a link to it in my slide. So, as I mentioned earlier, a ZMQ socket carry messages, not a stream of data. So each item is a discrete message that you can process and consume. All sockets do their I/O in a background thread. They don't block the main one. The Python binding does prevent a synchronous interface when you send and receive, so it'll wait for the receiving side or the sending side to complete that. There is an asynchronous library, and I'll show you a couple of the differences of working with that. And ZMQ sockets have 1 to n, however many nodes you want to be able to communicate with that socket built in. So, and you can build on top of that to do end-to-end routing, so you can have any number of nodes on either side of a communicating socket. I'll show that in a little bit. What is it not? It's not a built-in complete broker system like Celery or RabbitMQ or Redis. It provides the building blocks so you could build something like this, but it's a little bit closer to the metal. You can do a bunch of other things on top of it. as I mentioned, you can build a central broker on top of a larger protocol, and there is a whole specification in ZMQ for doing that. They call it the Majordomo protocol for being able to communicate and find and discover services and ask for something to be processed. It's not a neutral carrier. What that means is that a ZMQ socket, with some exceptions, you can't talk HTTP, SSH, FTP directly by itself. There is a stream socket that can connect to other services that implement those, but if you're going to use one of the built-in ZMQ sockets, you're not going to use a standard protocol. It's usually something that you are going to build yourself. We'll talk about the main messaging patterns. There are a few that can extend these to give you a little bit more functionality, but these are the main three that you would use in a ZMQ pipeline. The classic PubSub, a pipeline pattern, request reply, which I mentioned before, you probably want to steer clear of, but I'll show you what it might look like. So PubSub, one of the features of a ZMQ socket is that it doesn't care when things, you don't have to start up the server to be able to connect to it. You can fire up a client and it will wait until the endpoint that it wants to connect to comes online. So the way that plays out with PubSub is that if the main publisher starts up and there's nothing connected to it to subscribe, those messages will be dropped on the floor. It won't try to buffer them and queue them or anything, keep them in memory. It won't do any of that until it has a connected client to subscribe to that stream. If there's any questions as we go through, just go ahead and raise your hand. That we'll be building on each of these pieces as we go along. So, as I mentioned before, it's 1 to n, so any number of subscribers can connect to that. In the latest versions of ZMQ 3 and 4, the topic filtering is done on the publisher side so that the subscribers don't have to pull down a bunch of items to be able to filter it for the pieces that they're interested in. So when the subscriber connects, it tells it either no filter to get everything or a specific pattern that will be matched on the beginning of any messages that are sent on that socket. Then the filtering is done on the publisher side. The next major pattern is a pipeline where you use the push and pull sockets so that you have an entry point into your pipe, and then you can push it, and then it will fairly distribute each task to any number of connected workers. One of the things that a lot of people get tripped up on is that if your workers take a little bit to start up, a lot of messages could get routed to the very first one that connects. So sometimes people will put a pause in the entry point in the pipeline to wait for all the workers to be spun up and then start pushing it down the pipe. And then it will be fairly distributed against all the connected workers. And the usual result is that the workers will then deposit their results in a sink or collector to be passed on for further processing, or say pushed into another persistence layer.
In the last slide, you said messages can end up on the floor if no one subscribed to a topic.
Yes.
Here, what happens if there's no worker and someone puts something in that top.
Okay. So the question is, how are messages handled if a worker isn't connected to receive that? And in this model, it will wait.
Okay.
It will block the socket. Once a certain number of messages have been put on that socket, it will block, and the ventilator won't be able to push any more onto that. So there is the concept of back pressure, so that if you get too many, it will pause, and that will filter all the way down, so that if the sink, for whatever reason, gets swamped with too much data, it will back push on the workers, which will in turn push all the way up in whatever is the top level of that pipe. So here's a link to that Armin's post. The request reply pattern is lockstep, which means that the client will ask it for a certain item, and the server will reply to that. The problem with it being a lockstep protocol at the protocol level is that if, for whatever reason, the server goes down and comes back up, the client's going to be out of sync, thinking that I sent this request, I haven't gotten a response, and it will just wait. Or if the client goes down after it's initiated a request and the server's trying to send a response back to it, it'll error out because it's not in the correct state. So if you're going to use this pattern, you have to wrap both sides with exception handling for if one side has gone out of sync. So in more recent versions of ZMQ, they've tried to iron out some of the more common causes for if one side might go down. So it's, but there's still gotchas. So I wouldn't recommend it unless you really need it. So the interesting thing about ZMQ is the concept of transports. So you can easily, if you design your system, even if it's going to start out on a single box, you can sandbox different parts of that processing. And then if, as you're working and you see this part of the system really needs to be pushed out to its own box or another process, you can switch to a inter-process communication or TCP and push that out to a completely different box. Each ZMQ node is completely independent. There's no shared state between that. You have to use some kind of serialization to send data to either side. There is the concept of multipart messages to take a little bit of that load off, or you can send a single string that's JSON, protobuf, whatever you're interested in. So I'll kind of show a diagram of what that might look like. So if you have a client, it's just making a request to that router, which then the workers might be threads in a single process, or if you see that it's starting to need more processing power, you can push that out to a set of external processes that communicate using IPC, or push it out to a completely different box or set of boxes. So that's all transparent to ZMQ. There is a really good guide available on the ZMQ site that goes through all of this, and we'll talk in depth of every type of socket and how you can put those together to build a distributed system. So I highly recommend reading through that several times. It took me probably a week of just reading it, going back through, trying to work through a couple of the examples. They've done a really good job of showing examples in several different languages, so that usually with each example there's a link for, I want to see this, what it looks like in Python, I want to see what it looks like in Ruby, in Java, whatever. So you can work through and see that. This is the general process that we go through anytime we're going to start working on a new system that needs to consume our data. We sit down with the stakeholders and get a concrete list of what the system needs to do, and using any tool that is comfortable, pen and paper, some diagramming software. We just have a simple diagram, as I have shown a couple times, of how the data is supposed to flow through the system. And then we hammer out a hard list of the contract each step of the pipeline has to do. So it will take this type of data, consume it, do whatever processing, and emit whatever else on its socket. And then once we have that in place, I will build the shell of that system so that all the sockets are set up, all the event handlers, and then go back through, and whatever business logic needs to happen in each layer, we'll implement that. So I want to talk a little bit about how we as a team have evolved of working with the library as our level of activity has ramped up in different parts of the system. We first started out just using the Synchronous API, which obviously, once you hit a certain level of performance, it's going to start really sucking. It's just, I mean, you were going to be waiting for network communications, so it's a good first step to get your feet wet, but you will quickly move on to the asynchronous API if you have any real data stream. So I'll give some examples of each paradigm as we ramped up. So in each process or thread, you usually have this ZMQ context, and that context will basically have handles on any sockets that you want to communicate on. You give it the paths you want to connect to, what you want to bind, and then you just have this loop where you're waiting for somebody to come in on the socket, parse it, and then do whatever you need to with that message, and then send it on to the sending socket. So in this first step, you're going to wait for network communication to happen, and then do whatever you need to, and then you're going to wait for the sending side. So you can't receive anything more until this send has completed. So like I said, it will introduce latency into the system, but it's a good way to get familiar with how the different pieces interact. The next one is pretty low level. It's what the asynchronous bits in the PyZMQ library use under the covers. So this is just showing you, is really similar to what I showed before, but it's connecting to the different sockets, setting the subscribe option for that filter, the 10,001. That socket will only receive messages that have that prefix in it. And then the polar will register for events on that socket. Here, this is kind of the next step. I didn't have enough room on the slide, but here it's a similar while loop, but then you can wait for any event to happen on either of those, or if you have more than this number of sockets, you can wait for any event to happen on that, and then it will tell you which socket what that message was on. So you say, if that receiver is in the set of sockets that I've done something, I can receive that message, or if it was a different socket, you can receive that other one. So this is, like I said, it's pretty low level. It's really verbose. It's what the ZMQ stream code does under the covers. A lot of the configuration is mixed in with the logic of how things flow. So you've got your strings in the topic that you want to look at. It's mixed in with the actual handling of everything. The next step that we went to was using the ZMQ stream system. This is built on top of Tornado, so that slide that I showed before, where all this polling logic is abstracted on top of the Tornado event loop. So here we still have, we're just setting up the raw sockets, what connection transport we want to use. We're setting our topic that we want to listen to. And then we wrap the actual socket in this ZMQ stream, which does all the magic of polling on top of the loop. And here I'll show what it, and then you can just assign a handler for that. So the details of how the events are handled off the raw sockets are abstracted for you, and you can take advantage of the Tornado loop and add your own callbacks or anything on top of this. This is what we settled on for quite a while. The problem that I started to have with this is that it's hard to, if you need to track state between each set of your incoming or outgoing sockets, it starts to get a little bit unwieldy. So what I started doing was abstracting a lot of this type of code of setting up the actual socket and how I wanted to process that. And I developed an open source package called cscrowdstrike.erie, which looks like this. The Vassal is a top-level generic class that has some basic utilities for setting up database connections, anything that we need to use on every aspect of our systems. And then there is a ZMQ channel NameTuple where you can say the endpoint you want to connect to, what type of socket it is, all that configuration. So it's done at the top of the class. One of the things that bothered me as I was working through different areas of our system was that a lot of the details of, okay, where is this connecting, what socket, what path, if it's an inter-process communication socket, what path in the file system, it could be really hard to find where that might have been set up in someone else's code. So the reason why I like this is that it's at the top of every class, so you have a ready spot to look where any piece wanted to connect or send its data on. That is just an example of setting the filter that particular socket wants to use. So any message that have that filter, it could be any string.
And it's inside of a list, so that suggests I can put in a couple?
Yes. Yeah, you can have any number of filters that would then be routed into that particular socket.
Just string matching?
Yes. Yeah.
What's a Vassal in real life? What is that?
It's okay. I'll take a step back. The one of the fun things about starting a new project is trying to find some kind of naming system. Okay, so cs.erie. Erie is everything that we do at CrowdStrike usually has some kind of connotation of raptors, birds of prey, things like that. That's why you see our logo. Erie is the nest of like an eagle up on a mountain. So the Erie system as a whole is the final resting place for all of the data that our analysts will look at. So it's kind of the concept of the bird's eye view of the data as it's flowing through the system. So Erie is also the name of a fortress in Game of Thrones. So I don't know if there are any Game of Thrones fans. So I kind of went with that with how we name things. A vassal is just a generic term for someone involved in the feudal system. So at any level of, if I'm a serf, a worker, or if I'm a soldier or whatever, it's just a general term for someone involved in a feudal system. So, and then solid concrete implementations of that will have a specific title. So Scribe is the name of the class that's used for logging. So anything that comes through that, it will get written into files or things like that. Correct. Correct. So the question was, how was Erie spelled? It's Eyrie.
So is there a Joffrey Lannister class?
No. No, it's mostly just generic, what that type of person might have done in the feudal system. And here's just an example of, so in our code here, we're setting up the keys in the channels dictionary are then used. The vassal class will look for a handler for that channel. So it will map an input key to on input, and then the frames are what's going to be received on that socket. So the second socket is just subscription. So on subscription will be the event handler for that. It's just a convention that I've used. It could be extended so that the ZMQ channel could have like a handler or callback key to it, but the convention of matching up the name to this normalized name was easy enough. This is what I'll talk a little bit about later on, an example of what we like to do as a best practice, so that with the ZMQ stream, anytime you assign a handler, it's basically going to be an example of a multi-part message, so that you are always going to get a list in your callback. And we've had instances where if we change what the format of the data that we're going to send, we might send an additional element. The downstream, somebody might have forgotten to update the downstream consumer, and now all the indexes are off. So what we use are NameTuples, so that it will unpack that frames, and then you can use actual names as attribute access for accessing that data. So I'll quickly running out of time. I'll fly through these best practices. I'll get these slides up so that you can see them. A big one is keeping pipelines as short as is practical. If your pipeline gets really long with each step that you want to do, it can become really difficult to figure out what part might be failing. So as I mentioned before, I get the shell set up first, and then you can see logging messages. So if one set in the pipeline isn't working correctly or isn't passing the data as we expect, then you can see the smoke coming out. So some sort of process control app is necessary, either Supervisor or Circus. You're going to have a lot of different pieces that are implementing different parts of the pipeline. And I just want to put a shout out for PiPI. It is really mature. There's been a lot of work to make it truly perform.
As opposed to old-fashioned C Python?
Correct. Just by switching from CPython to PiPi, it doubled the throughput in one part of our application.
Why?
Just the JIT engine just really does a very efficient job of like unrolling loops, things like that. It really is a solid piece. This last item, that you want to make the ventilator or the collector be really dumb. They just do really simple things, pushing things out to their distribution set. Any deserialization or serialization of the data you want to do in the workers, because the top and bottom of the pipeline are usually just a single process. So those can quickly become bottlenecks if you try to do too much in those. As I mentioned before, there's no shared state between nodes, so you're going to be paying a serialization, deserialization cost at each step. So like I mentioned before, you want to keep your pipeline short. Using multipart messages with NameTuples to document the structure of the frames of that message is really helpful. Here's an example of a NameTuple. So you define the name of the class, and then any attributes that will be mapped to the input side. And then if you're going to send it, you can use kwargs for the logger name or message, and then on the receiving side, it'll be unpacked as a tuple. Multipart messages are great for simple messages, but as the keys might skyrocket, you want to use a true serialization format like protobuf or JSON. And I would highly recommend not to sacrifice the ZMQ portability by using something like Pickle. Because if you get to a spot where the workers are really performance critical, you don't want to have to go back and change your serialization format to something that the worker might be implementing in Go that it could speak.
How do you handle dates in JSON? Is that a problem you deal with a lot, or time?
So the question is, how do you handle dates in JSON? I generally use on a Python DateTime object just the ISO format, and then that's usually pretty standard. Any other language can usually parse that pretty straightforwardly. So here's the example that I was mentioning before. This is the really performance critical. This is accepting the fire hose of data from Kafka. The example with the ZMQ router, any number of nodes on the left can map to any number of consumers on the right. So we use 2 consumers usually on a box just in case. Usually one is strong enough to saturate like 8 downstream workers, but we usually just have 2 polling just in case. So this system was pulling from SQS on Amazon. It was only able to do 3,000 to 3,500 events per second. And as soon as we switched it over to pulling from Kafka, it was easily doing 30,000. That's more of a testament to Kafka than SQS. But this pipeline was able to process a lot more. It was just SQS that was the bottleneck.
Amazon's SQS?
Yes.
Have you experienced the thing where it delivers the same message to multiple consumers?
So the question is, yeah, so has SQS delivered the same message to multiple consumers? I haven't seen that. Our biggest thing was just that the the throughput was just horrible.
I
Like,
think the docs state that the contract is will deliver it at least once.
Yeah.
So they say that.
I've seen that one. Yeah, it drives me crazy.
So with Kafka, each of these consumers will pull from a specific partition so that the top one doesn't see the partitions that the bottom one is pulling from. And then if you have multiple boxes, like we have 3 sets of this set of pipeline running, pulling from Kafka, so that's a total of 6 consumers. They split 100 partitions in Kafka, so they're all processing a different set of the pipeline as it's coming through. And then this is the last step of the pipe. By the time the Raptor framework has consumed that fire hose, it's whittled it down considerably. There's usually only maybe tens of messages a second that reach this stage. And this is where our analysts at the final end, once business rules have been applied, adding tags so that we know if this message is coming from this client box, we want to mark it as high because we know that they have an active intrusion that we want to be notified of. It'll be shipped off to Postgres and eventually shown in an Ember.js UI. Elasticsearch does a lot of our indexing, and we use it a lot for aggregating the data so that you've got faceted filtering at the top. Just a set of links for reading more. This is the CS Erie package I mentioned. It's in a very in its infancy. There's not a whole lot of documentation. We were able to split it out from our code, so it's all generic, not really specific to us. Are there any questions?
What do you have in place for testing, as far as like ensuring like contracts between the various queues and stuff like that? Kind of like I guess not necessarily unit tests in place, but integration testing.
Yeah. Unfortunately, not a whole lot at this point. The main thing that we've been able to try to use throughout our name tuples to, if we need to change the format before a downstream worker can consume it, that allows them to, if they always use the attribute access versus the index in the tuple, it can mask that for a little bit until we can get around to updating that section of the code.
I have 2 questions. The first one was in the pipeline mode, you were saying that it distributes it fairly. How does it actually, what's the process that it does that? What if one of the workers is held up longer, or the job that it's given is much longer than an average job? What is it actually doing to load balance that? Is it like a round robin, or?
As soon as the downstream socket says that I'm ready to accept that, it will distribute to that. So the downstream worker will pull it off of the ZMQ socket and just wait for it to be processed. The ZMQ has a concept of a high watermark. So if there are too many of those, it will say I'm full and communicate that to the other side and say, okay, I won't send any messages to that particular worker. I'll start sending them to different ones.
Okay. And then the second question I had was about the asynchronous push-pull.
Yes.
So for that, when you're doing the on-receive, is it grabbing multiple messages at once, or is it just one message, or I guess that's just the whole question.
Well, what if your handler will only get a single message at a time? So that frames that I mentioned before, it'll be a list, but it will consist of a single message at a time. So your handler will only ever deal with one thing at a time.
Okay, I think that's it. Thank you very much, David.